Let's recap what we discussed when we were relating linear motion with angular motion. In linear motion, the associated displacement is xb minus xa. In angular motion, we can find the displacement by finding the change in theta b minus theta a. The straight line from A to B is the displacement in linear space. This can also be found, but we're not going to be using it at the present moment. Instead, we will be focusing on the arc length, which is depending on the radius multiplied by the change in angle. So this side will be the linear motion, and this side will be the angular motion. The velocity is given by the change in x over the change in time, and an equivalent equation for the circular motion will be given by the change in theta over the change in time. You can basically use also the derivative. Things get a little bit interesting when we get to acceleration. Now, acceleration for the straight line motion is basically the change in velocity over the change in time, or similarly you can basically say acceleration d squared x over dt squared. Alpha will be given by d omega dt, and I'm sure you can also note that that will basically be d squared theta over dt squared, and that's your alpha. Let's dive a little bit deeper into the acceleration. It's something that you're swinging around a circle in the particular direction. The object would have to be kept inwards by centripetal force. And some of you might also be thinking, when the string breaks, the force that is basically that apparent force that you actually think is going to be pushing it up is actually called the centrifugal force. Now, this force basically doesn't exist. If you think about it, the object is not going to be flying straight that way. It will just try to go tangential to the circular path. Now, let's go back to talking about the acceleration. The angular acceleration is given by the change in angular speed over the change in time. Here are the accelerations that you need to think about in circular motion. The tangential acceleration, I'm just going to call it AT, and centripetal, I'm just going to call it AC. The centripetal acceleration is actually given by omega squared r. The tangential acceleration will be given by angular acceleration multiplied by the radius. This is the same as the change in velocity over the change in time, because this is acceleration. So the total acceleration of this object as it goes around the circle will basically be given by the tangential acceleration plus the centripetal acceleration, where tangential acceleration is always perpendicular to the centripetal acceleration. Let's say we've got 3 masses that are hung on a string. I'm sure you can actually agree with me to say all of them will cover the full revolution in the same time, so the angular velocity is the same. Okay? Here now we're going to look at the mechanical energy. Okay? And again, we're going to relate the linear motion with the angular motion. kinetic energy, or EK, in linear motion is actually given by half mv squared. Things get a little interesting when you get to angular motion, where the mass of the object actually changes. The mass of the object get replaced by something more befitting, like what we refer to as. Now, in angular motion, a similar equation can be used with what we refer to as angular rotational inertia. Now, before we delved into these two examples, before we delved into more details about this, I just want to give you a quick and interesting, I just want to give you a, you need to remember that the mass equivalence in rotational motion is basically what we refer to as the rotational inertia. Now, rotational inertia is basically the tendency of the object to change or to resist the change in rotational motion. But in formulas or in calculations, for linear motion, we will literally just use that mass m, and for rotational motion, we will use what we refer to as rotational inertia, which is I. Now, let's just make an example there. Now, in linear motion, we would say that the kinetic energy EK is half mv squared, and in the equivalence of that equation in angular motion will basically be EK, which is equal to half I instead of mass. And then what is the equivalence of velocity in angular space? That will actually be your omega. So that will be omega squared. So please just note that slight difference. Similarly, you can basically talk again about EP, which is the potential energy. What is mg or ax, right? So that will be your potential energy. Now, in rotational motion, we normally just say EP is equal to m. We know the equivalence for mass is basically the rotational inertia. And what is the acceleration? Rotational acceleration or angular acceleration, we use alpha for that. And then what do we change? In linear motion, we change the position x, and then in rotational motion, we know that we are changing the angle. So that will actually be theta. Can we say the same about power or mechanical power? Yes, we can do that. We would actually say then that the power, I'm going to use letter P for this, in rotational motion or in linear motion, it will just be the energy. In this case, I'm just going to use max, and then we just divide that by time. So that will be the formula that we normally use then for calculating power in linear motion. In rotational motion, we just do the same. We would say just power is equal to rotational inertia multiplied by the acceleration, which is alpha, theta, that we divide by t. Now let's just go a little deeper with this. I'm sure you can notice that the force in this equation is given by that portion over here. So that will be your force, right? And what is the change in velocity? And this one here is basically the velocity. So then this equation can actually just go down to saying this will be the force multiplied by the velocity. That will basically just be the force multiplied by the velocity. Let's then talk about the power. So for power, which I'm going to just write as P, in linear motion, we basically just say it's actually the work at the rate of doing work, right? I'm just going to put just the potential energy there as MAX, and that divided by the time, which then it will be easy for you to notice that we are actually multiplying the force by x over t, which is your velocity, okay? And similarly, in the rotational motion or in angular motion, we can basically just do the same, but I just need to bring something to your attention here. In rotational motion, okay, we don't look at the force that is actually applied. We look at the force and the perpendicular distance, meaning the turning force, and that turning force is actually referred to as the torque. Okay, now here we go. For the rotational motion, we can again do the same thing and say power is equal to okay, and then we will realize that the theta, the t, is basically the omega, which is the velocity. So this part over here is basically the angular speed. And we multiply that with the force, which is rotational inertia multiplied by the angular acceleration. So then we use the torque instead of force. It will basically be torque multiplied by angular acceleration. Okay, now remember, torque is the force multiplied by the perpendicular distance. Okay, or you can simply just see that because this is a dot product, you can see this is the force times distance cos of the angle between them. In the next video, we are going to look at some few exercises that have to do with. In the next video, we're going to look at some few exercises about the very same topic. In the next video, let's talk about the period and the frequency. When you have an object that goes around a circular path, let's say it starts somewhere there at 12 o'clock, a period T is the time that it takes to complete a full revolution, and the units for that will be in seconds. Similarly, we can also look at how many times the object rotates or completes full revolutions in 1 second. This is the number of cycles in 1 second. If an object revolves 3 times around the circle in 2 minutes, calculate its period and frequency. So now we'll start first with the period. Period is basically the time. And what is the time? We said that it's 2 minutes, and 2 minutes is 2 times 60 seconds. And how many cycles did it take? It took 3. So that will basically be 40 seconds to complete 1 full revolution. What about the frequency? The frequency is the reciprocal of the period, the number of cycles, which is 3, divided by the time it took to complete those cycles, which is basically 2 times 60 seconds, 0.025 hertz. We can also write the period T as 2 pi over rotational speed, or the rotational or angular velocity.